Have you ever walked on a completely flat ground where every step feels the same, no climbing, no descending? That's similar to what we call an equipotential surface in electrostatics. In simple terms, an equipotential surface is a surface where the electric potential remains constant at every point. Mathematically, we say delta V equals 0, that is, delta V equals 0. Now, here's the interesting part. If you move a test charge along an equipotential surface, the work done is 0. That's because the electric force doesn't oppose or assist your motion. It's like walking sideways on a hill instead of up or down. From vector physics, we write this as E dot dl equals 0, where E is the electric field and dl is the displacement vector. And most importantly, these equipotential surfaces are always perpendicular to the direction of electric field lines. Imagine a diagram with circular surfaces around the point charge, each one a shell of constant potential. Different charge arrangements create different shapes of equipotential surfaces. For example, a single point charge, say a positive charge, produces spherical equipotential surfaces around it. All points at the same distance from the charge have the same potential, and when you place two large parallel metal plates with opposite charges, the field between them is uniform. Here, the equipotential surfaces look like flat sheets stacked like pages in a book. Let's recall the potential due to a point charge. It's given by V equals 1 divided by 4 pi epsilon naught multiplied by Q over R. That's V yards 1 4x pxe0 x Q R. This equation helps us understand why the surfaces are spherical. Potential depends only on distance r from the charge. And the closer the equipotential surfaces are to each other, the stronger the electric field in that region. That's why in diagrams, the denser the surfaces, the more intense the field. Let's go deeper into the behavior of these surfaces. One key point: electric field lines always intersect equipotential surfaces at right angles. Why? Because there's no component of the electric field along the surface. Now, can two equipotential surfaces intersect? The answer is no, and here's why. If they did, that single point would have two different potentials, which is impossible. Remember, the electric field always points from higher to lower potential, and the steepest descent happens perpendicularly to equipotentials. We also know that the work done in moving a charge from point A to point B is W is equal to Q multiplied by VA minus VB. But on an equipotential surface, VA equals VB, so work done is 0. Let's now connect this to real life. Imagine you're looking at a contour map of a hill. Each line represents the same height. That's the same as an equipotential surface in electrostatics. Just replace altitude with electric potential. In electrical systems, metal conductors, like wires or aircraft bodies, are often equipotential surfaces. Any excess charge distributes itself in such a way that the entire surface is at the same potential. A powerful example: the metallic body of an aircraft acts as an equipotential during flight. Even during a lightning strike, the charge spreads instantly, keeping passengers safe. And in capacitors, each plate is an equipotential surface, maintaining uniform voltage across its entire surface. So equipotential surfaces are not just abstract physics, they are engineered into real-world systems. Let's solve a numerical to strengthen our understanding. Problem: a test charge of 2 microcoulombs is moved along an equipotential surface around a point charge. The displacement is 5 centimeters. How much work is done? Let's solve this step by step. Step 1. Recall the work formula: W equals Q into delta V. That's W equals Q times delta V. Step 2. Since we are moving along an equipotential surface, delta V is 0. So, W equals to microcoulombs times 0 volts equals 0 joules. Answer: No work is done when moving a charge along an equipotential surface, no matter how long the path is. This reinforces our understanding. It's the potential difference, not distance, that determines the work done. Let's quickly revise what we've learned about equipotential surfaces. They are regions where electric potential remains constant, meaning no work is required to move a charge across the surface. They are always perpendicular to electric field lines and never intersect with each other. Around a point charge, these surfaces are spherical. In a uniform field, they are flat planes. From aircraft safety to capacitor design, equipotential surfaces play a crucial role in how we control electric fields in technology. I hope now you see how such an elegant concept helps us visualize the invisible forces shaping electric behavior. Keep your curiosity high. See you in the next topic with another powerful idea from the world of physics.